Good day, everyone. I am Maureen Season.
And I am Lalaine Jambalina, together with our groupmates Atienza, Bobadilla, and Makalindol.
Today, we will present our case study titled Bhopal Gas Release of 1984. The Bhopal disaster is widely regarded as the deadliest industrial accident in modern history, and it remains a critical example in the study of process safety engineering, instrumentation reliability, and industrial risk management. The incident occurred at a pesticide manufacturing plant operated by Union Carbide India Limited in Bhopal, India. During the accident, a large quantity of metal isocyanate or MIC escaped from the facility and spread across nearby residential communities. In this presentation, we will analyze the disaster from an instrumentation and control engineering perspective, focusing on the system design, engineering practices, safety instrumented functions, reliability failures, and the engineering improvements that could prevent similar incidents in modern chemical process industry. For our system description, the system analyzed is the metal isocyanate storage and handling system at the Union Carbide India Limited Pesticide Plant in Bhopal, India. The facility produced carbaryl pesticide using metal isocyanate or MIC as an intermediate chemical. MIC was stored in three underground tanks, the E610, E611, and E619, each with a capacity of about 68,000 liters. The tanks were kept under a nitrogen blanket to prevent contamination and were typically maintained at around 50% capacity. A refrigeration system kept the MIC between 0 and 5 degrees Celsius, while a circulation pump maintained consistent cooling. MIC was transferred to the production reactors through a piping system equipped with bulbs and monitoring instruments, with vapors directed to a process vent header. Safety systems included a vent gas scrubber, a flare tower, a water curtain system, and pressure relief devices designed to control hazardous releases. For the engineering practice analysis, the engineering practice analysis highlights several issues in system design and operation. The plant stored large amount of metal isocyanate, which increased the potential hazard. In some cases, storage levels exceeded recommended limits. The refrigeration system was designed to maintain MIC at low temperatures, but it had been shut down prior to the incident, reducing temperature control. Operational practices also showed weaknesses, as some safety systems were inactive or under maintenance. In addition, monitoring of key parameters such as temperature and pressure was limited. Although the facility had several safety barriers, their reduced functionality limited their effectiveness in preventing or mitigating a hazardous releases. For the SIS evaluation, here is the range.
For Safety Instrumented System, SIS, evaluation the plant's safety instrumented system included the pressure relief system, the vent gas scrubber, the flare tower, and the refrigeration system. Each function was intended to prevent or mitigate hazardous releases. However, this system lacked full independence and shared utilities, which made them vulnerable to common cause failures. Many safety actions depended on manual operator intervention rather than automated control. While multiple safety layers existed, they were not fully redundant because they relied on common equipment paths, reducing overall system reliability. For reliability and safety impact at the time of the disaster, Several critical safety systems were non-operational. The refrigeration system had been shut down. The flare tower was disconnected for maintenance. The vent gas scrubber operated at reduced capacity, and instrumentation alarms were unreliable. The simultaneous unavailability of multiple safety layers prevented early detection and mitigation of abnormal process conditions, allowing the MIC runaway reaction to escalate and release large quantities of toxic gas into the environment. For engineering improvements focus on reducing chemical hazard and improving reliability. Hazardous chemicals such as MIC should be produced and consumed immediately rather than stored in large quantities. Modern safety instrumented system with automated shutdown logic and SIL-rated instrumentation should detect abnormal condition and initiate protective action automatically. Redundant safety barriers such as dual scrubbers and backup flare system should be installed to ensure protection if one layer fails. Finally, a structured preventive maintenance program including regular inspection, functional testing, and calibration of safety critical equipment should be implemented alongside routine and hazard analysis, such as HAZOP studies. That's all for Bhopal Gas Disaster 1984.
Thank you.
Thank you.